Dear colleagues, good morning. Let us start our morning session. But before we start, let me ask our organizer, Vladimir Petrov, to say some words to speakers.
Well, hello and good morning, everybody. I have something to say, very short. Today is a kind of a very special day because we have many people and many speakers which, so to say, the philosophical incline. And I would like to ask all the speakers to remember that the audience just filled with people who can hardly distinguish between ontology and epistemology and so on. So you have to remember that normally the majority of those who will listen to you, they are not very skillful in philosophical questions. So my suggestion to you is to try at least to be as simple as possible, as elementary as possible, having in mind that the people who are listening to you are not expert in many fields of philosophy and history you are going to present. Thank you very much. Thank you.
Okay, thank you. I'd also like to remind the participants that all the questions after the talks should be neither lengthy or of discussion character, and I ask all the participants to postpone such questions to our evening discussion session. Now it's my pleasure to invite the first speaker, Olivier Minazzoli. Please share the screen.
Okay, hi everyone. Can you hear me well?
Yes.
Or should I use a headset?
Yes.
Okay, great.
Fine.
Okay, thank you very much. Thank you for the invitation. So yeah, I'll try to be as simple as possible. So today I'll talk about a new general theory of relativity, which we named entangled relativity. The name entangled has nothing to do with quantum entanglement, but has to do with the fact that the formulation of the theory is such that you cannot define the theory without defining matter at the same time as curvature. And therefore, in the etymological sense, they are intertwined together. And it turns out that this new general theory of relativity turns out to be more parsimonious than general relativity. Okay, so first of all, I will, I will recall a few potential issues of general relativity. The first issues is the issue of singularities, whether inside black holes or in the primordial universe. As you all probably know, this theorem from Roger Penrose shows that whenever there is a formation of an event horizon, then eventually you'll form a singularity, and this is bad because it means that the very laws of general relativity breaks down, and therefore it leads to this paradoxical thing that general relativity predicts objects within which it cannot be defined everywhere, and this is really paradoxical. A lot of people believe that this should indicate a breakdown of general relativity, and this would be cured by quantum gravity effects. This is I would say, the consensus today. Another issue of general relativity is when you merge it with quantum field theory, is that space-time does not seem to have an operational meaning beyond the Planck scale, meaning that whenever you want to probe really short scales, like the Planck length and the Planck time, it would require such an amount of energy that you would form a black hole, and therefore you don't get any information from at those scales. So it really seems to indicate that there is no operational meaning to the notion of space-time at the Planck scale. And more generally, the different quantum gravity programs have a structural modification of space-time at those scales, at the Planck scale. Either the smooth or the continuous structure of spacetime seems to have to be modified at those scales. Not all of them, not all the quantum gravity programs. For instance, in asymptotic safety, that's not the case. Okay, and the final issue that has been debated a lot during the 20th century, but not so much during the 21st century, is that inertia can be defined from nothing in general relativity, meaning that general relativity does not satisfy Mach's principle of Einstein. So what is this principle? Basically, this principle states that there can be no space-time without matter. And so the reason, please mute yourself if you just joined okay, thank you. The reason why Einstein imposed this principle is for philosophical reasons. As Vladimir said, a lot of people will talk about philosophy today, so this is one of the philosophical issue. So for Einstein, it does not make sense to even talk about emotion without matter surrounding it, because if there's nothing, there is nothing to which you can compare your motion, and therefore there's not even a point of talking about emotion. Okay, so for Einstein, motion is relative, and therefore inertia is relative. The issue with relativistic theory is that as soon as you have a space-time metric, you have an inertial structure, because the inertial structure is given by the metric. And therefore, in a relativistic theory, if your theory allows for a vacuum solution, that it means that you can define a motion with respect to nothing, if not space-time itself. But Einstein was trying to get rid of an absolute nature of space-time a la Newton when designing his relativistic theory. And therefore, that's the reason why he thought that satisfactory theory of relativity should have no vacuum solution. Okay. Now I'll talk about the phenomenology, first of all, the formulation of the theory, and then its phenomenology. So the theory entangled relativity is nothing but a simple reformulation of general relativity, where instead of assuming a linear coupling between the Ricci scalar and the matter Lagrangian, you assume this very specific nonlinear coupling, and we will explain that during this talk. The first thing that you can notice is that here you have a coupling constant kappa, whereas here you don't have any. Okay, I have to stress that this theory and what I will present today relies on the work of many different people, starting a decade ago with Aurélien S, when we were both at pretty much at the same time at Caltech JPL. And we found decoupling that is at play in this theory. It was in a different context though. Okay, so that's the path integral formulation of the theory. And the reason why I show the path integral rather than just the action is because I want to evaluate this guy here. We'll see what it is. So if you look at what is inside this integral here, this has the dimensionality of an energy squared. Okay, so in order to have a quantum phase, you have to divide it by an energy squared. So you know that this guy here is it's a quantum of energy. Okay, so that's the only parameter of the theory, and you don't know what it is a priori, but we will evaluate it during this talk. So it's a quantum of energy. So the good thing with the theory right away is that you can see that it does not make sense to consider the theory if you don't have matter, because if matter does not exist, then the theory does not exist. So that's the real reason for the name that we gave to the theory, is that matter and spacetime and space of curvature are entangled at the level of the formulation of the theory, meaning that they are intertwined. They cannot be treated separately, unlike in general relativity, where you can have derive the laws of general relativity in vacuum, and you have non-trivial solutions to that. Here is not possible. But so it solves this issue of Mach's principle. although it was for philosophical reasons. So maybe, well, it looks like something interesting, but maybe it was not that important. So that's the first thing. So now, when we look at this path integral, the first reaction that I get usually, especially from the particle physics community, is that this action cannot make sense, because if you assume that you can neglect gravity, then R is constant. If not zero, that would be even worse. And if that is the case, then you have element squared. And obviously, this is not standard physics, okay? Because it's not element squared. Besides, when you have a square, you would expect theoretical problems such as the Ostrogensky instability, the Cauchy problem wouldn't be well posed, stuff like that. But those comments turn out to be naive. And the reason is because they assume that we know what gravity, what is the meaning of neglecting gravity. But the thing is, here, the theory is not general relativity. So we don't know what it even means to neglect gravity here. So before being able to neglect gravity, we have to study what gravity is in the theory. And this is what we'll do now. Okay, so it turns out that there is an equivalence between this nonlinear action on the left-hand side with this scalar tensor theory action on the right-hand side, where kappa here is a scalar field that couples to both the Ricci scalar and to the matter field. This type of action is often called an Einstein-Dilaton theory, because in reference to the string dilaton, because in the lower energy effective limit of string theory, you often have a scalar field that couples to both the Ricci scalar and to the matter Lagrangian. And more generally, whenever you have theories with more than 4 dimensions, you have this kind of action. Okay. So it's a bit like in FOR theories. For those of you who know FOR theories, you know that there are equivalent to a scalar tensor theory with a potential, where it's pretty much the same thing here, except that we don't have an FOR theory. We have a generalization of that. It's an FOR LM theory, but it turns out to be equivalent to this Einstein-Dilaton equation. Okay, so the correct way to show the equivalence is to derive the whole field equations from the left-hand side and from the right-hand side and show that they are the same, including for matter fields. But there is a really quick and dirty way to figure that out directly. Indeed, if you externalize the action with respect to kappa here, the solution is this constraint equation here, kappa equal minus R over Lm. And you simply reinject that back into this action and you get the first action, okay? This is written here. And this shows that they are the same on shell. Okay, so this is a quick and dirty way to figure out that they are indeed the same. But of course, the good way to do it is to derive the whole field equations. Okay, because of this equivalence with this scalar tensor theory, the Cauchy problem is well posed in the theory. And this actually can be figured out pretty quickly. Let's assume that you have a scalar field as a matter Lagrangian. Then you can do a conformal transformation, and then the action that you will get is general relativity in addition to 2 scalar fields that are coupled to one to the other. So this is perfectly, there's no problem with that. Okay, so this is the metric field equation of the theory. You see that there is this additional term on the right-hand side here. And it turns out, because of this non-minimal coupling here, the nonlinear coupling or this non-minimal coupling here, you have a non-conservation of the stress energy tensor. And usually this is bad, because usually it means that the theory won't be viable at the observational level because it will predict things that we don't observe in the universe. But that won't be the case here. As usual for FOR theories, you get the differential equation on the scalar degree of freedom by taking the trace of the metric field equation. So the trace of the metric field equation is given here. So that's the equation on the metric on the scalar field degree of freedom. Okay. Okay, reminding that kappa is equal to that this ratio between R and Lm. So second comment that I often get is people saying that, but wait a minute, if Lm goes to 0, then kappa blows up, and therefore the theory does not make sense, because it could be the case that Lm goes to 0, at least locally. And And that's not the case. And for pretty much the same reason as in general relativity, the ratio between R and T does not blow up when T goes to 0. Why is that? Is because the trace of the metric Einstein equation imposes that R is proportional to T. And therefore, when T goes to 0, R goes to 0 at the same rate, and therefore the ratio is perfectly well defined. Actually, it is a constant in general relativity. So the same thing happens here in entangled relativity. One has to keep in mind that this equation here, the ratio, is not independent from the other equations. And especially the differential equation that governs this value, the value of this ratio is given here, okay, by equation 9. And if T and Lm are 0, then this equation is not sourced, and therefore it's a perfectly well-behaved equation when Lm goes to 0. And therefore you should not expect anything special happening to this ratio when Lm goes to 0. So that's for the intuition, but we can verify that with an exact solution. The charged black hole solution of this theory. So it's given by this metric here. So when the charge goes to 0, then R minus goes to 0, and you recover the Schwarzschild metric, okay? Obviously, when Lm goes to 0, when the charge goes to 0, Lm goes to 0 as well. But so does the Ricci scalar, because after all, matter field, the space-time curvature has been made by matter, okay? So it is dependent on matter as well. And in a way that the ratio is perfectly, you can see, you take the ratio between the two, and you can see it's perfectly well defined when Lm goes to 0. So there's no issue with Lm going to 0, and as it should have been obvious from the start, given the equation at play. Okay, because you have this scalar tensor theory form, you can do a conformal transformation, as I mentioned already, and if you assume that you only have an electromagnetic field, then you recover the unusual Einstein-Maxwell dilaton theory, where the value of alpha here is different for different theories. So for this specific theory, entangled relativity, alpha would be equal to 1 over 2 square root of 3, whereas for a bosonic string, alpha would be equal to 1, and for a 5-dimensional Kaluza Klein theory, where one dimension is compactified, alpha would be equal to square root of 3. Okay, but if you know a little bit about the theories, you should know that they are highly constrained by observations whenever alpha is not close to 0, or if you don't have a potential for the scalar field. So if the scalar field is massless, then alpha has to be really close to 0. And that's not the case here, because alpha is less than 1, but it's not really close to 0. So how come that I seem to believe that the theory is nonetheless viable at the observational level? The reason is because this theory lies at a really specific point in the space of theories that is such that there is an exact cancellation in the field equations. This is what we'll see now. So we call that an intrinsic decoupling with my friend Aurélien S. a decade ago. And this is how it works. So this is the equation on the additional scalar degree of freedom, okay? So whenever it turns out that the on-shell matter Lagrangian is equal to the stress, the trace of the stress energy tensor, and what is the on-shell matter Lagrangian? For instance, for electromagnetism, the matter Lagrangian is proportional to F squared, where F is the Faraday tensor, but on-shell for a pure magnetic field, for instance, it would be proportional to B squared, whether for a pure electric field, for instance, it would be proportional to E squared, and for radiation, it would be equal to 0 on-shell. Okay, so that's the specific value that the Lagrangian takes when you inject back the actual field solutions. Okay, so whenever Lm is equal to T on shell, then the additional scalar degree of freedom equation is not sourced, and therefore it can be a constant. Kappa being constant is solution of the field equations. And for this solution, obviously, this is equal to 0. You cover the equation of general relativity, and this is equal to 0, and therefore you cover the conservation of the stress energy tensor, and therefore you recovered general relativity minimally coupled to matter. Okay, so now the question is, when does that happen? Well, it happens that we have Lm is equal to T. It happens, for instance, for a universe that would be entirely made of dust with electromagnetic radiation, because for dust, the on-shell matter Lagrangian is just the sum of the masses times c squared, okay? Whereas for electromagnetic radiation, the on-shell matter Lagrangian is equal to 0, whereas the trace of the stress energy tensor is also equal to 0 because electromagnetism is a conformally invariant theory, okay? So this is good because it means that for a universe like ours, that is well approximated as being made of dust with null radiation, you shouldn't expect the theory to deviate much from general relativity. That's at the qualitative level, the reason why you recover general relativity with the theory. So we not only worked at the qualitative level, but also at the quantitative level. It's a really new theory. So there's a lot of things that remain to be done and remain to be studied. But the first studies go in the right direction. So we found out that for a universe made of dust and electromagnetic radiation, the scalar degree of freedom freezes, and what gets general relativity back at a cosmological level. And the reason for that is because the expansion of the universe introduced a friction term in the scalar field equation, and therefore it freezes the scalar field where it was, irrespective to its previous dynamics. Neutron stars are at max a few percent more massive than the ones of general relativity, and this is free of any, we don't have any free parameter in the theory. So it is parameter free. The exterior solution of spherical black holes cannot be distinguished from the ones of general relativity in astrophysical condition, meaning when the charge goes to 0, because astrophysical black holes are not charged or are not expected to be charged. So that was for spherical black holes, but now we also have the demonstration for slowly rotating black holes. And because of this equivalence with Einstein-Maxwell-Dieterson theory, we can use works from in the literature showing that the gravitational waves emitting from the fusion of two black holes would be the same as in general relativity, as long as the two black holes have not significantly different charges. And since astrophysical, we don't expect black holes to be charged at the astrophysical level, it means that we should not expect deviation from the waveforms of general relativity from this theory for the merging of black holes. That could be different for the merging of neutron stars, but this remains to be studied. Okay, so basically the broad consequence of this decoupling is that this ratio here turns out to vary very much less than the variation of the spacetime metric. Okay, and this if you are bothered by that, remember that R over T in general relativity is a constant. So it is not actually that surprising that this ratio becomes a constant or is close to be a constant. Okay, so that means that quite generically, this nonlinear weird-looking action that we started with, which turns out to be equivalent to this more usual action, you can simply neglect the variation of kappa and take it out of the integral. That would be the case, for instance, in the solar system. If you evaluate the variation of kappa in the solar system, you will see that it is perfectly negligible for every kind of experiment that we have in the solar system. And therefore, for the solar system, you can just take it out of the integral and you recover general relativity. So that shows why general relativity is a limit of this theory, but moreover, it's a predicted limit of the theory. It is predicted by this intrinsic decoupling that I've talked about earlier on. Okay, now let's come back to quantum field theory. So what is quantum field theory on flat spacetime? It's quantum field theory when gravity is entirely neglected, because as far as current physics goes, a flat spacetime does not exist in nature. It is only a good approximation on scales where gravity can be neglected. Okay, so when you neglect gravity if you take the core theory of physics, you entirely neglect gravity, and what you end up with is the path integral for the standard model. Okay, if you neglect, so now coming back to the original question that we had, what it means to neglect gravity in this theory. Well, it means that both you can neglect both the variation of G, the metric, and the variation of this ratio. And again, I recall that R over T is equal to 0 in the core theory of physics as well. Okay, so when you neglect the variation of the two, then you end up with this this path integral. And now, in order to recover a standard quantum field theory, you have to identify the two. And by doing this identification, you are able to identify the value of this, the only parameter of the theory, this quantum of energy. And this quantum of energy turns out to be the Planck energy, to be the reduced Planck energy. Okay, so it's a bit like in general relativity. In general relativity, you have this coupling constant kappa, which is not given by the theory, but because you want general relativity to recover Newton physics at the leading order, you have to impose that kappa is equal to 8 pi g over c to the fourth. Okay, so it's the same thing here. Because you want in this limit where you can where you neglect entirely gravity, you want to recover standard quantum physics. Basically, you have to impose that epsilon is the Planck energy. Okay, so now you can see through this identification that here in this equation, there are only two constants, one on the right-hand side, epsilon, and one on the left-hand side, c. Kappa is a field, and therefore h bar is not a constant. And the quantum of action is not a constant. And this should have been obvious all along, because never a quantum of action appeared in the formulation of the theory, meaning that obviously it was not fundamental, but it is more emergent in some limits. It's emergent in the limit where gravity is classical and can be neglected for the phenomena that you're considering. Okay, but that's really interesting, because then it means kappa is 8 pi g to c to the fourth. Then it means that in this theory, the quantum of action h bar is proportional to the constant of Newton g. That gives an explicit connection between the quantum world and the gravitational world. Moreover, it means that in this specific theory, the weak gravity limit corresponds to the classical limit. So the reason, whatever that reason may be, if g goes to 0, h bar goes to 0 in this theory. And I think this is pretty interesting. So I said h bar varies, but you may be worried because it seems weird. And I'll give now an evaluation of the variation of h bar, the numerical evaluation of the variation of h bar. So this is a simulation for a neutron star, which I remind you are the densest objects in the universe that are not hidden behind an event horizon. So the variation that we will get for h bar in this context is the biggest variation that you could expect for h bar in the observable universe. And we'll see that it's only at the percent level. So that's the variation of the scalar field phi, which is proportional to the inverse of h bar, or maybe to the square root of the inverse, I don't remember, but it's a normalized value. And you can see its variation here. So the scale is given here. The vertical line is the radius of the neutron star. And you can see that the variation is only at the level of a few percent only. And actually, between the surface of the neutron star and the remote observer, it's less than 1%. Okay, so that's the maximum level of variation that you could expect in the observable universe for h bar. It is at the percent level, so it's really small. But you can see that the scale of this variation is several kilometers, meaning that for any quantum phenomenon at the surface of the neutron star, for instance, that the phenomenon that would produce the X-rays emission, for instance, you can perfectly assume that h bar is constant, the same way that you assume that the metric is Minkowskian for this specific quantum phenomenon. Okay, so now something I believe that is really interesting is that since you only have two dimensionful universal constant, being the causal structure constant, usually named the speed of light, and the Planck energy, that means that you don't have enough dimensions in order to construct a Planck length or a Planck time, meaning that those notions do not even exist in this theory. And I would argue that this is circumstantial evidence that this theory does not have the same issues as quantum general relativity at the Planck scale. These now have to be studied carefully, but I think this can be taken as circumstantial evidence that it won't be the case, and that probably in the theory, spacetime can be an elementary, the smooth and continuous spacetime can be an elementary structure and can be valid to any scale. But this has to be studied, of course. Okay, now the final point is the issue of singularities. So from the field equation, you can see that the kappa being negative is not prohibited in this theory. Okay, we've seen that in the observable universe, kappa will always be positive because the variation, the level of variation of kappa is at max at the percent level. Therefore, you don't expect kappa to vary more than that. But a priori, it is not impossible that in even denser environments, such as inside black holes, or maybe in the primordial universe, kappa becomes negative. This is not prohibited. Although maybe it doesn't work that way, because maybe if you study the field equation, you will find that if you start with initial conditions that are such that kappa is positive, then kappa will always remain positive all along. Or the other way around, if you start with initial conditions such that kappa is negative and therefore gravity is repulsive, then you will get propagation that are such that kappa will always remain negative. So this has to be studied from a mathematical point of view in order even to know whether that's possible to have that kappa change its signs. But in principle, it is possible, and this is something that I think might be interesting either for the primordial universe or inside black holes in order to potentially resolve the singularity issues. Okay, so now that's a wrap up. So this theory is a simple reformulation of the general theory of relativity that turns out to reduce the number of universal constants. Okay, instead of 3, we have 2 constants only. It turns out to recover general relativity and standard quantum field theory in a generic limit. It has no elementary length or time scales, and has no free parameter at all, which is pretty unusual in the field of alternative theories. Okay, because it does not have any elementary length or time scale, it may indicate, or it might indicate, that spacetime is not doomed after all, unlike what is often believed in the current physics community. And it does not have anything exotic. It's just a simple reformulation of general relativity. And it makes a clear prediction that is that h bar can vary depending on gravitational phenomena. And I hope that we will be able to prove that in a foreseeable future. And this would be a smoking gun in favor of this theory. And I'm done. Thank you for your attention.
Okay, thank you very much for a nice talk. Please, questions. Teryaev, Oleg, please.
Well, thanks for an interesting talk. And I have a question related to Mach principle, which you mentioned as one of the cornerstone of your approach. And there is example of Mach principle in general relativity, which is discussed actually in the textbook books of Weinberg and Misner-Thorn-Wheeler. And this is corresponds to Lenz-Thirring effect. So if one consider massive rotating shell and the rotator inside, classical rotator, and just it's possible to generalize this to also to quantum rotator, when if the ratio of say gravitational energy to rest energy going to 1, the precession frequency of the rotator inside is equal to rotation frequency of shell. and I believe Weinberg wrote that it is probably what Mach means by his principle. So just its rotation, and why one cannot see this rotation. My question: can you consider this particular example in your approach and see whether, in this case, Mach principle is valid?
Okay, so first to answer to this specific question, well, I would have to solve the equations for because the field equations are different, so the work has to be done basically. But in principle, you can see whether the solution works or maybe another solution with the same type of behavior. But I would say that the issue with Mach's principle in general relativity, I think it's really philosophical because so I think the real issue with general relativity is that it allows for a vacuum solution, which would not be Machian.
No.
But some people may say, but okay, but we don't care because we have matter in the universe, and therefore, even if general relativity has vacuum solution, does not exist in the universe because we have matter in the universe, and therefore we're perfectly safe from the Machian point of view, because, for instance, in the solar system, you have to your metric has to be attached to the cosmological background metric, and this is how you get this Machian realization in general relativity. Nevertheless, I think that it is still an issue for general relativity because as soon as it allows for a vacuum solution, it means that you have an issue with I would say, the ontology of inertia or rotation, because the Kerr solution is a vacuum solution and it's rotating, but it's rotating with respect to nothing. And you cannot have a Kerr solution is different from a Schwarzschild solution, meaning that there's no way you can change your coordinate system in order to transform a Kerr black hole into a Schwarzschild black hole, meaning that for a vacuum solution, the rotating property seems to be intrinsic, whereas in the universe, rotating property is relative. And therefore, there are two different ontologies for rotation in general relativity, whether you're in a vacuum spacetime or you're with matter. And I think this points toward an inconsistency of the theory. But this is philosophical, so I believe so. But and so when we found this nonlinear action here, that's the first thing that we realized, is that we cannot have a theory without matter, and therefore we directly thought about this Mach's principle, but this was not the motivation for the theory.
Well, just I fully agree that typically Mach principle is philosophical, but I mentioned a particular case where it is practical, and this is and that's why I think it can be interesting to address this practical Mach principle just in also a different approach. So just maybe I think it can be indeed, and this is really interesting issue related to indeed to rotation, and sometimes this issue is practical, but this is indeed the point addressed by in these two textbooks and addressed in some detail. I think it's interesting. I think it's interesting test ground where philosophy meets really physics. Thanks.
Yeah, thank you for your comment. There are so many things that remain to be done in this theory. Where basically pretty much everything remains to be done because it's obviously a new theory.
Thanks.
Okay, thank you. I think we have time for more questions, maybe from audience. No. If not, let me thank the speaker again